Hello everyone. I'm happy to introduce our speaker of today, Dr. Yefim Gitterman. Yefim is a senior seismologist, project manager, and seismology division of the Geophysical Institute of Israel. He completed his PhD in Engineering Sciences, Seismic Studies, Institute of Mining, Siberian branch of the Academy of Sciences, Novosibirsk, Russia. And before his employment at the Geophysical Institute of Israel, he worked as senior research fellow at a Mining Blast Seismic Laboratory, Polytechnical Institute, Magnitogorsk, Russia. Research interests are analysis of dynamic features of seismic and infrasound waves from explosions and earthquakes, and development of discrimination methods, design and conducting of large-scale underwater, underground and surface explosions for calibrations of IMS stations, observations and analysis of air blast waves from surface explosions and water shock waves from underwater explosions, and evaluation and reduction of seismic hazard from explosions and earthquakes. Yefim was awarded by a large number of awards, like Phillips Laboratory U.S. Department of Energy Award, U.S. Department of Defense Award, and the U.S. Army Space and the Missile Defense Command Award. Yefim serves as representative of Israel in European Mediterranean Seismological Center and as representative of Israel in an intergovernmental coordination group, Northeastern Atlantic, the Mediterranean and connected seas, as natural tsunami warning focal point. Please.
Thank you. Good afternoon to everybody. I'm glad to be here for the first time to give a lecture, hoping that you like it, and maybe it's not the last one. I chose for this presentation one of the most interesting experiments that I conducted many years ago, 16 years ago, November 1999. It was a number 3 underwater explosions in the Dead Sea. So 3 half-ton, 2 tons and half and 5 tons underwater, with the main goal. What was the goal of this experiment, of these explosions? It was calibration or tuning seismic station of IMS, International Monitoring System. International System for Monitoring Nuclear Explosions. It's shown here on this map. And different symbols show different type of stations: seismic stations, infrasound stations, hydroacoustic and radionuclide. And all this system, including now more than 300 stations, works with the goal to identify any nuclear explosions with size more than 1 kiloton in any place of the world, if it's underground or underwater or in the atmosphere. What is calibration tuning? To explain what is it, this is, for example, this is Israel Sinfonietta Beersheva, where my wife plays for more than 30 years. Here it is on viola. And before the concert, before they start playing music, the first violin give the note la, and hautboy, and then first violin give all the time the note la, And everybody, all musicians know that he will give this note, and they tune their instruments according what they hear. And then if they tune their instrument, they can perform the music as necessary. And the same is the calibration of seismic station or infrasound or another. When we give this calibration explosions, then we know exactly its time with accuracy less than 1 second, with coordinates with accuracy several meters, and exactly know its size. So this station, remote station of this network, can be tuned, and then if in the case of any explosions that are known or any other event, they can identify and estimate parameters of this event accurately and reliably. So this experiment was conducted in the framework of the United States Department of Energy project. It was a competitive research grant. And why was chosen this media underwater? Why not underground? Why not in atmosphere? Because underwater explosions, we'll show later, provide much more higher seismic effect, much more seismic energy than underground, or of course explosion in atmosphere. Now, the place choice, why the Dead Sea? Why not Mediterranean or any other sea? Because no life in the Dead Sea. And there was one case when scientists, seismologists want to conduct similar underwater explosions in the Atlantic near Portugal, 6 ton, and everything was ready. They purchased explosives, rented the ship, everything, but it was publication in the media and green protest, and they canceled all this experiment. So the second reason, it's the unique properties of the Dead Sea water. Super saline water in the Dead Sea, providing the highest seismic effect, more higher than in usual water, oceanic water. And for example, the density in the Dead Sea, 1.236, acoustic velocity 1,770, opposite to much lower value in the ocean, the usual seawater. Nevertheless, no life in the Dead Sea, but we met a number of hard problems. The first, it was environmental problem, because many people say that there will be a damage to the unique mineral springs in Ein Gedi. Another problem, safety vibration. A number of hotels in Ein Bokek area, about 30 kilometers from the planned explosion site. Another problem, seismic hazard. Some people thought that large-scale shots, and they placed exactly in the Dead Sea fault system, tectonic system, that most of earthquakes in Israel occurred along this tectonic system. And so there is a hazard that maybe these explosions will trigger a strong earthquake. Also, the last one, the political problems. It was very close to the border between Israel and Jordan. And we were urged to get a permission from Jordanian authorities. And through the diplomatic channels, we got permission from the King of Jordan. It was a special document. But on this reason, that there was many problems, so we planned, actually what we need, it's the largest explosion, 5 tons. It was the major. But before, to check all our estimations and to check if there are no some damage to nature or to buildings, so we started with half ton and then 2 tons explosions before the main shot. This is a map of this area in northern part of the Dead Sea, and explosions was done. This is bathymetric map, and it can be seen that at that time, 1999, the water surface was minus 415, and the depths of the sea at this point was about 250 to 160 meters. And we deployed a number of seismic sensors along the Dead Sea in order to monitor seismic ground motion during the explosions. There was a lot of preparation. It was a rather large project. It was several countries participated in this project, and several private companies. And all sea operations was provided using the ship Echelot, maybe somebody knows, Lot's Life, was many years ago, and we use it for sea operations. And also the raft, the steel raft, that was used actually mainly this raft because after the first explosions, half ton, when the ship was rather close to the explosions, the captain find that there is a leakage in the ship, and so decided that it will not be, and next explosions will be much far distance, and so we use this iron raft. So we can see here towering the raft of the explosion site, submerging 5-ton charge here. It was long preparations. On this picture you can see the rather complicated configuration of this experiment and charge design, when the charge depth was defined as 70 meters. 70 meters is rather deep, that most of energy will be go to the seismic effect, and it will be the optimal seismic effect from these explosions. And we use also a number of buoys and cables and raft here. And this is a charge. The explosives were placed in plastic boxes, dolevs, and we used a special waterproof explosives, Hanamon, and as main blasting agent, and cast TNT as the booster. We observed during these explosions very interesting phenomenon related to physics of underwater explosions, and one of the main physical feature is bubble effect. Because when we have spherical explosion on the depths, so after detonation of explosives, a lot of gases produced, and they start to, the bubble of gas begins to expand and then shrinks due to pressure, water pressure, and again expands, and we have pulsation of the bubble gas, and in rising to the surface, and little by little decreases in radius. And what is important in this process for us is the period, the bubble period, fundamental period of this pulsation. And we used this, I hope that it's very simple empirical formula. Only one, I will show only one more, where depending, this period depending of course of the charge rate and on depths or barometric pressure on the Dead Sea level and densities in the Dead Sea and in ocean water. And so for the explosion, for the second explosion, for example, it's little more than 2 tons. The period was 0.6 second, and it's important, we will see. And for the largest explosion, 5 tons, it was about 0.8 second period of bubble pulsation. Okay, the first explosions was on 3 o'clock local time, 8 November 1999, 500 kilometers, and this is area view, and we can see this white plum on its cavitation head. It's also special physical phenomena. It's formed by reflection, when shock waves from explosion reflect from the surface. Then it creates small gas bubbles, and we can see like foam, because this head, it's named cavitation head. So, this is from the airplane aerial view of these explosions. And now the second explosion, 2 tons, was also about 4 o'clock. And we will see during this video that usual video, not speed video. We can raft. The video camera was on the raft, 775 meters. And we also will see cavitation head and shock waves that arrive to the raft and give shock on the raft. And all this during the first second. And then uprising of water, when gas bubble arrives to the surface, and we can see uprising. Video snapshot of these explosions show evolution of the cavitation head. We can see different 60 millisecond, 120, and so on. And also this cavitation head created direct shock waves. And also interesting that we can see on this 440 millisecond, 0.44 second, we can see the focusing of camera. And this time, the shock waves arrives to the raft, and camera defocusing, and we can see next, after about half second, again defocusing. And this is related to arrival of the bubble pulsation. The second bubble arrives, shock waves from the bubble pulsation arrives, and this about very roughly estimation, half second, and it's close to the measured value and also close to the value obtained by the equation, the formula. Okay, this is the most interesting, but the largest one. I will show this separately because through the PowerPoint it's not going. I have a problem. Just a moment. if you hear 3 times, yeah, yes. So it was very impressive. You can see the buoy on the top after 5 seconds, 6 seconds. The steel buoy, this very large, is more than 2 meters length, size, and we can roughly estimate the height is about 15-20 meters of the surprising, and also we can see the cavitation head. Yeah, and when we used spectrogramma, from this video, use soundtrack, the acoustic channel. This is its record, and then spectral analysis, spectrogramma in frequency time domain. We can see very clear this peaks, and it's with a difference time about 0.8 second. And this exactly correspond what we heard, and it corresponds to the bubbling effect, bubble pulsation. Now it was these explosions were recorded by all stations of Israel seismic network. Here from Hermon up to Eilat. Here the explosion, and all stations recorded all explosions. And we can see also in usual FFT Fourier spectra very clear modulation due to bubbling pulsation. And using this estimation of maximum, we can rather accurately estimate period as 0.78. And it's very close to the values that are obtained from equation. Here also the spectrogramma of this of the same record at Eilat station. Eilat distance 200, more than 200 kilometers, and spectrogram strips show the spectral modulation due to bubble effect in decreasing high frequency energy in time. Here these strips for more high frequency energy, and we can see that they shorter, so in time decreasing. Also we measured shock pressure in water from the water shock waves with a special equipment, and we can for the large 5-ton shot. We can, it is a record at distance more than 600 kilometers of gauge was near the raft. The raft was placed on this distance. And we can see here the straight direct P phase. This is time in second, and this is pressure in kilopascal. Very clear direct waves and reflection from the surface. When shock waves arrive to the surface, or reflected as with negative pressure, negative phase. And then also other phases related to propagation in water and in the bottom. Yes, here record of water shock waves from second shot to 2 tons, and it was measured by 2 gauges, 2 sensors that placed at about 20 between 25 meters, about 25 meters between, and so we could estimate the velocity of shock waves in water, and we found it 1,794 meters, and this is a little more than acoustic velocity in Dead Sea water. And the reason that there was very high pressure, and shock waves in higher pressure propagates with higher velocity. This plot shows the demonstrate very high effectivity explosions in the Dead Sea water. This is lines. It's theoretical or based on empirical equations for the ocean water for 2 tons distance, pressure in megapascal, for 2 tons and for 5 tons. And once it's experimental, our measurements, and we can see, and this, if it was, the explosion was TNT, at TNT at higher energy explosives than we used. And we can see that actual pressure go higher than for the same equivalent, for the same weight TNT exploded in seawater. About 30–40% higher values for 5 tons here and for 2 tons. So it's due to unique acoustic impedance. Density and high velocity, higher than in ocean water, we observed that acoustic impedance more than 40% higher than in the ocean, and so we also pressure obtained about the same increasing. Now magnitudes, a very important parameter of any seismic events, explosion or earthquakes. Its magnitude. You know that when an earthquake occurs, everybody say 4.5 on scale Richter or 5.6 or 7. And so the same we estimate for explosions. And so there is a relationship between charge weight and magnitude. And this black line, it's for explosion underground in rocks. And the blue line is for explosions in water. And this for explosion in supersaline water of the Dead Sea. And we can see that it's much higher, larger magnitude than in for underground explosions. And for 5 tons we obtain about 4, magnitude about 4, at very high magnitude. Magnitude 3.9. About 4 people that were observed at several kilometers on the seashore felt very good the ground shaking, and also it was observed at very large distances. I show now. Yes, it's all stations that observed seismic waves from the largest explosion. The largest was in Russian stations placed at about 5,000 kilometers, the largest distance, the more remote station. And also there was a number of stations in Europe and Middle East and Saudi Arabia. Actually, we obtained data for this station, Saudi Arabia, through our American colleagues. And more important, it was observed at 8 IMS stations, 8 stations of information monitoring system. Okay, after the first explosion, 500 kilograms, there was a paper in Maariv about this explosion, and this Avi Shapiro, head of our seismological division that time, and he was also principal investigator of the whole project. I was manager of the experiment. Avi Shapiro was, and of course, who gave an interview to the paper. And after this paper, there was some people, Minister of Environment, told that we have to, I cannot see, that it's very dangerous, that maybe it should be cancelled, the next explosion should be cancelled, and we were very anxious. We don't know if we will be allowed the next explosions, but finally it was decided to do it. And that's also interesting publication in Arabic press. During our experiment, we know that that possibly in Arabic countries there will be some accusation of Israel that they made nuclear explosion or something like that. And for this reason, we invited a number of international observers. There was observers from the United States, from Russia, from Jordan army. There was senior officer presented all the time during the experiment. And nevertheless, after sometimes in Arabic press there was publication that Israel conducted a small nuclear device, 5 tons, for development of weapons and so on. So one of publication okay. So this was a successful experiment. It was unique, and since then I didn't hear that anybody in the world, somebody made similar explosions, similar experiment, provided a lot of observation, not only far regional seismic observation, but also some very interesting close near source observation and interesting effect. And so it was useful for calibration of regional seismic station of international monitoring system, used for monitoring of nuclear tests. Obtained data that we obtained in and results in this experiment were used later for analysis and interpretation of different other underwater explosions, and particularly for the tragic accident with Russian submarine Kursk. It was a couple of years after this experiment. And also recently, several years ago, there was an accident with South Korean military ship Cheonan, and also for analysis of data, seismic acoustic data from this experiment, we used data and results that we obtained in this experiment. Maybe it's a separate topic, separate lecture, and maybe in the future, if you like, I will in the future also present some interesting result related to the sea. The most interesting, because I actually conducted also some explosion, very large-scale explosions on the surface, not in the sea, several years ago. But it's also a separate topic for presentation. Thank you.
Thank you very much, Yefim. Any questions, please?
I understand that there are quite a few stations recorded this explosion, and the data was given back to you. Was it used for crustal and lithosphere studies? Did you use the data, the recorded data, for crustal and lithosphere studies?
Yes. They data, seismic data recorded at our station were used. Dr. Vladimir Pinsky uses data for improvement and modification of the crust model in the area of the Dead Sea. Yeah, but I cannot now tell you more details about it, but for sure that were used together with other explosion experiments. data from other waves.
Other questions? Okay, so just I wanted to ask you, when you demonstrated a movie about the explosion, so I didn't understand the details, the processes. First we saw the a peak, and then the waves started to go to spread around this place. So about how this bubbling is can be seen in this picture.
On the video we cannot see bubble. On video we can hear, we heard, yeah?
Yeah, but which
acoustic.
process? Yeah, but which process is connected to this bubbling?
It's related, the bubbling effect produces special features of seismic waves.
I see.
That in seismic waves, because we have here the very famous, well-known effect, physical effect, interference, wave interference.
Okay.
So we have wave from the direct wave, and then another wave with a delay for the bubble expanding, and so interference produces this modulation effect in seismic waves.
Okay.
But actually this effect of spectral modulation also used for identification of explosions, underwater explosions, because we in our practice, when we record seismic waves from different seismic events, we have to decide this is earthquake or this is explosion. Because for analysis of seismic activity, we had to to extract all man-made events from the catalog. And so if you know that events occurred in the sea, here in the sea, so it can be here, we know that there are Carmel faults, and there is a number of earthquakes here, or another place. And so we have to decide, it is an earthquake or explosion. But when we make, we analyze records, seismic records, and make spectral analysis, and we see the spectral modulation, there are 100%, we can say that it is explosion, underwater explosion. So it's used also in discrimination or identification of seismic events.
Okay, but for instance, if it is underground explosion, so you don't see, you don't have
if underground explosions, we don't have
yes,
bubbling effect and don't have spectral modulation. If it's simultaneous explosion, like this, here also simultaneous, all explosives exploded simultaneously, but because due to pulsation of the bubble, we have the spectral modulation. If these 5 tons we explode in the ground, so we will not see spectral modulation. But if we have explosion, quarry blast, so technology of quarry blast, modern technology, they used millisecond delays between different parts of explosives. They used millisecond delays. And then we also can, because also we have interference of seismic waves, we can also see, this modulation, spectral modulation. So it's also the very good parameter to identify the quarry blast,
okay.
like underwater explosion.
Okay, thank you. Any other questions, please? Okay, thank you very much, Yefim, for your talk.